Great, thank you so much. So, Paul, you forgot to mention that I'm also working for Xanadu, but that's fine. No, I'm joking. So welcome from me. I'm super excited. I'm a bit nervous as well because I'm having a bit of Wi-Fi issues, but I think you should all be able to hear and see me. If I'm lagging, just get a cup of coffee, but we should all go through this. What we do this morning in the first couple of talks is basically introduce you to the core concept of Penny Lane, and that is quantum differentiable programming. And so the next couple of talks will basically circle around this concept. What I want to do to kick it off is give you a very high-level introduction, after which I hope, you know or you have an idea of what quantum differentiable programming is, how it fits into near-term quantum computing, how it fits into Penny Lane a little bit. And secondly, I want to tidy up with a lot of words and lingo. So the lingo of Penny Lane, the lingo of this hackathon, the lingo of quantum machine learning and near-term quantum computing. So I want afterwards you to know what is automatic differentiation, what's a near-term quantum computer, what's a remote device, what's VQE, what's an embedding, all of those things. But I don't have a lot of time, so very high. Wonderful. Okay, cool. So this is the lingo on one slide. I tried to keep with a trashy like QHack kind of theme here. So I want to go through three areas. I first want to go into differentiable programming. So if you have quantum differentiable programming, there has to be a differentiable programming. I want you to understand how it relates to optimization, automatic differentiation, why gradients are so important everywhere, and how it relates to machine learning. Because Penny Lane is a quantum machine learning library in two senses. You can do quantum machine learning with it, but it's based on principles that come from machine learning. So this is quite important. We then jump into quantum computing, and those of you who listen to quantum computing introductions all the time, you know, like might be a bit scared here, but I won't start really with everything of what is a qubit and so on and so forth. I basically just give those who haven't heard much about it just a way to think about it and clarify a couple of things like terms of near-term fault tolerance, simulators, hardware. And in the end, I want you to know what is a trainable quantum circuit. And then we go to applications, and they've got for you quantum machine learning, quantum optimization, and quantum chemistry. Okay, cool. How to outsource thinking to gradients. That's differentiable programming. And I thought those terms I wanted to explain, I actually found them in the first couple of sentences on Wikipedia, and that was fantastic. So I'll just read this to you for now. Differentiable programming is a programming paradigm in which a numeric computer program can be differentiated throughout via automatic differentiation. So here we've got automatic differentiation. This allows for gradient-based optimization. That was a term I wanted to teach you. Of parameters in the program, often via gradient descent. There we've got the gradients everywhere. And differentiable programming has found use in a wide variety of areas, scientific computing and artificial intelligence. And these are kind of the applications that we have a lot. So I start explaining this kind of statement from the bottom up. I'll give you an example of basically a little program that we want to do. I'll show you how it can be solved with the idea of differentiable programming, how gradients come in. Okay, let's think of the task. I want you to code up basically a program that evaluates a function. So here, just a sine function with an offset at an arbitrary point x, so that it is guaranteed to have value y1 at point x1. So this is not entirely arbitrary as an example. I mean, it is a bit random, but because it is this idea of machine learning and also of scientific computation in the terms of we've got a function with parameters. So scientific computation, you could have, I don't know, an approximation to Navier-Stokes equation that depends on some parameters. And then you've got some data that you know you want to fit this function to because you know the data is something that reality has observed. So this is like where this is motivated. I know you could do two things. You could think, and I know physicists especially and like scientists, they love doing the thinking approach. So a solution could be coded up just by taking in all of those four different inputs and then basically just computing by hand what are the parameters that verify this like data input-output relation. And there you could say like, oh, the offset can be 0, and then we can just invert the sine function and we get kind of the right output. This fails, obviously, if it comes to machine learning or very big Navier-Stokes equations or anything that's larger. And in particular, it's not very flexible because, so if you've got a huge neural network, I read recently that neural networks these days have 200 billion parameters sometimes. So if you just change one little bit of the algorithm, then your thinking approach doesn't really work. So even physicists have to kind of start outsourcing. And the idea is here, let the computer figure it out. And I cannot explain enough how much of a change in thinking. This is of computation as such. And this change in thinking is here. I define a cost function because I know I want the output of my function be close to y1. So I can just, for example, take the difference and square it. And then I optimize the cost function. So this is like outsourcing thinking to optimization. So why gradients now? So there's lots of ways to minimize this function, and there are lots of optimizers coded up. But in machine learning, in particular, when you have a lot of parameters, you're in such high-dimensional spaces. So by space, I mean now, here the space will be AB, so two-dimensional space. But in such high-dimensional spaces, you need information of some sorts. And gradients provide you that information. So what is the gradient of our cost here in this example? It's just the vector of partial derivative of a function value with respect to its parameters. So what information does the gradient give you? Most of you will know this. It points you in this parameter space, so this is this plane here, towards the direction where the cost function has its steepest ascent. So gradient-based optimization algorithms just go the opposite direction of the gradient, and usually they go in small steps. So this is why you have training steps, epochs, iterations. So now we kind of had like a little example from here, and we know like, okay, gradients are needed. But what about automatic differentiation? And again, here I'm just touching upon it. It's actually a lot more, it's actually really deep. If I read papers on automatic differentiation, I don't even understand the first sentence. But in like the easiest iteration, automatic differentiation means that a computer program knows how to compute gradients of functions. And if you look at the function that we just had, in a computer, it's actually a chain of functions. So you have a product, you have a sine function, you sum something to it. In fact, you can draw it as a computational graph. And those of you who do a bit of TensorFlow coding, for example, they know that there was a change from a computational graph mode to an ego mode. So automatic differentiation libraries sometimes actually explicitly represent computations as these graphs. And the cool thing about this is if we represent it this way, we can just use a chain rule of taking the partial derivative of the cost with respect to a parameter and just like basically taking partial derivatives on the way of these functions with respect to their inputs. So if a computing library knows what's the partial derivative of a square root with respect to its input, it can, in theory, compute through huge, huge pipelines that contain a square root function. And so there are lots of automatic differentiation libraries. I plot here only those that Penny Lane supports at the moment, but if you have requests for other ones, like please just let us know. This one up here might not be so familiar to like people who do machine learning or hardcore automatic differentiation. It's NumPy's extension Autograd. And it just means like it's a wrapper for NumPy that you know. So NumPy has a sine function, NumPy has a sum function, but it just registers basically gradient functions with NumPy. And JAX and PyTorch, which is highly used in the machine learning community, they've got a lot of like GPU support and things like that, are actually based on Autograd. So I forked this package at some stage and just developed it further because it's unfortunately discontinued. So for us in Penny Lane, this is just like the beginner's package, so to speak. And then you also have TensorFlow that's very well known. Just to show you that this is really like happening in these libraries, I'll give you a little JAX example. So you can import JAX, you can import NumPy through JAX. So this is this wrapper, basically doing this Autograd thing. And now if you compute basically, if you use a function called grad in JAX, and you can throw in another function that you have from this NumPy, from this JNP NumPy, what this function that you create here does, it's the gradient function. And we know that the partial derivative of a sine function is a cosine function. So I just checked the two of them here, and you always see this assert statement is true. And then in Torch and TensorFlow, it works a bit differently. So if you've experimented, you know, in Torch, you always have to register parameters or inputs, whether they need a gradient or not. And then you kind of do your computation. Then you do this backward step, which is basically registering the gradients, and then you can get the gradient of a variable. So it's a very different thinking that's behind this in some sense, or design decisions. And in TensorFlow, you know, you have this tape. So it's just also like a different idea that registers gradients, but they're basically just doing the same thing. And now here's the crux. So as long as you can provide a gradient of a computation, you can slot them into differentiable libraries or automatic differentiation libraries, which means if we tell TensorFlow, PyTorch, and JAX, or Autograd, what a quantum computation is and what a quantum computation's gradient is, we can use these libraries and extend everything that is there about machine learning and bigger than machine learning, differentiable programming by quantum computations. And this is the core idea of Penny Lane: provide gradients and then dispatch computations to different backends to give you either like the output of your circuits, quantum circuits, or to give you gradients. And you can do this in arbitrarily large pipelines. And I remember Josh, who's our lead developer, most of you will know him from answering everything on Slack and GitHub all the time. So I think he had once a problem not too long ago. He wanted to debug something, and then instead of just debugging and thinking about what was wrong, I think he just differentiated through something and found the solution this way. So it's really everything in Penny Lane should be differentiable at some stage. This is our idea. Okay, cool. So now gradients of quantum circuits. And here we have to do a little bit of basics, but not much, unfortunately. But I'm sure you've all read a lot about quantum computing and quantum circuits when you're prepared for this. So this is probably for most of you trivial, but I just want to tidy up with this idea of near-term versus fault-tolerant quantum computing. Because if you say something like, what is a quantum advantage of ABC? The answer can be very different depending on which regime or which approach you have. Fault-tolerant is what people have developed quantum computing for in the last 30 odd years. So the idea is you don't have to be stingy with qubits. You've got millions in theory. Your computations are accurate because you can correct errors. So you don't have physical imprecisions that kind of multiply over time. And then these algorithms that you've heard of, Shaw, Grover, HHL maybe, they can all run on these like larger devices. But also there's an interesting idea in research how it's approached. So if you ever want to write a paper in the olden days of quantum computing or in the fault-tolerant regime, you have to argue that your quantum algorithm has a computational complexity that has a speed up. And that really changed in the near term. So a whole different type of researcher almost emerged. So here we've got like these noisy circuits, they're small, it's really hard to write algorithms for them. This is why these variation circuits that I get to now are basically the workhorse algorithms of them, because they do exactly this trick, figured out. So if I can't code up an algorithm because I only have so little qubits, I don't know what makes sense, just let the cost function figure it out. So that's why this trick is so important in near term. And then if you're the type of guy who just loves to run things and see, and this is also the idea of Penny Lane, enable a lot of people to just run it and see and do research with these things, then near term is like maybe the approach that suits you best. Also quickly, you can distinguish between, so Penny Lane has a lot of devices. We hear about this just now, but we distinguish between hardware and simulators, and then there are local and remote devices. Your local simulator is just you download, for example, Penny Lane, and you run something with default qubit, and it just like runs the code on your computer, or for example, Amazon Bracket plugin. There's a local simulator you just run on your computer. Remote is obviously like you send it somewhere and it's run on another server there, but it's also a simulation. Here, just a heads up, if you have around like below 20 qubits, you could be faster with your local simulator because there's a huge overhead, which is, the community is slowly decreasing this overhead, but it still takes often a couple of seconds or at least 1 second to send jobs. So if you send every circuit at once, it doesn't really, so you have to have really a very large circuit to have a speed up here. So everything large, then you can run remotely. That's often better because things are very parallelized up there. And then obviously the hardware is usually remote unless one day we have computers with a little quantum chip, which I don't know exists yet. Okay, now a couple of like words about circuits. And my goal is not to teach those who have never done quantum computing. I hope there's no one who has never done quantum computing at all. And if there is, then heads up. This is very courageous and very cool. Good luck. No, I'm joking. It will be good. So if you've done, so I basically just want to introduce this graphical notation that I'm using to make a few statements from now on. So quantum circuit is usually based on n qubits. The mathematical description of these n qubits is a 2 to the n dimensional vector, interpreted as a bookkeeping vector that tells you something about probabilities. And what it tells you about probabilities is that the absolute square value of these entries is the probability of a specific configuration of measuring these qubits at the end. Then circuits are mathematically modeled as unitary transformation. Most of you will know this as well. And unitary transformation just gives you a different state vector somewhere. Sometimes you hear of matrices here. So these are just density matrices. So there is a matrix representation of states as well. But the easier one is the state vector one. And now measurements, and this is important, quantum measurements always sample something. So measurements are never deterministic results unless your probability distribution is just weirdly shaped. So in most measurements, you sample bit strings from your quantum computation. And then often in variation circuit, we're actually not considering, strictly speaking, I mean, we always talk about this as being a quantum circuit, but we're actually considering something else as the quantum circuit, which is a mixture of classical and quantum processing, and which is to take lots of measurements, so repeat your circuit over and over. I try to show this with a stack symbol, and then average. And the mathematical description of this is basically this like vector times matrix times vector product. So this is a scalar. And lastly, most of you know that quantum circuits don't come in big blocks, although you can in Penny Lane like hack this in somehow, but usually you define gates that are local. And then basically trainable circuits, the whole idea is just make a couple of these blocks or these gates dependent on parameters. And then you will constantly hear, we're talking about Pauli rotations. So you can talk about this in general, but people usually use Pauli rotations as parametrized gates. And what you have here is now a quantum computation. It's actually a classical quantum computation, a hybrid, but this quantum computation is now parametrized, so you can train it as much as you could train the sine function with A and B. Okay, now just like a few words, but you hear this in a talk just now, a bit in more detail, about quantum gradients. I want to show you with this, like, oh gosh, now I'm doing maths with pictures. I don't know what you think of this, but like, I want to show you why it's not totally trivial to say a quantum computation can just have a gradient and you can plug it into automatic differentiation. And the idea to show this is this. Let's say you have a gate that depends on theta. When you have this expectation value, the theta appears on this side and on this side, just by how the math works. If you take the partial derivative with respect to theta, you just use the product rule as anywhere else. So there's no magic in quantum computing in that way. And that means you get a sum of two terms. And now here's two problems. The first problem is this is not an expectation value, and this is also not an expectation value because there's something else on the right side and on the left side. So this is not how they work. The second problem is that this thing here that I call like a gate is now a partial derivative of a gate, and we don't know if that is again a gate. So we do not know if this formula can be actually implemented on a quantum computer. And one of the big successes of variation circuit is that we can actually, in many, many cases, especially when we have these Pauli rotations. In this case, we have so-called parameter shift rules, just that you've heard this once and seen it once. You have a computation, your gate depends on a parameter. You can usually, and most of you might have solved it already actually in the challenges. You can just shift the parameter to the right and once to the left. This is not a finite difference rule. The parameter can be macroscopic, and then you combine the results. So this is important. We can get gradients of quantum computations by just running very similar quantum computations. And then lastly, just also you've heard this one because this is very hot in research. Everyone's talking about barren plateaus. It turns out, and there are lots of ways that barren plateaus can evolve. In this case, we just like have a model where we have a circuit before and after two gates that depend on parameters, and these circuits are randomly sampled. And then you can often show that if the number of qubits increases, the optimization landscape, so this is now here, this f is now my cost function, gets flatter and flatter. Why is this a problem? Because we don't really know where the gradients lead us. The gradient will be very, very short and will vanish in most of the cases. So this is a problem, but there are lots of solutions, very active field of research. And now lastly, just to come.
Well, looks like Maria's internet might have started acting up. We thought this might happen. I'm going to try to fill the void a little bit here while we see if she can come back right at the best part 3 applications. So disappointing. I was getting so excited for the rest of this talk. Maria's internet is spotty at best. Oh, I think she's starting to come back. I hear her. Maria, are you still there? She's there.
Yes.
I see some slides. Okay, you froze up just at the start of part 3.
Okay, cool. Did you get your coffee break? That was a very quick coffee I had to have there. Okay, cool. No, I should be fine. Okay, yeah, there's nothing as my worst nightmare is Wi-Fi issues, but I'm almost done here. So yeah, quantum chemistry. So basically we've got a couple of applications. Hope they can pay for what we want to build. Quantum systems or chemical systems are in some sense so microscopic that they're quantum systems, and they are modeled by Hamiltonians. I know that Hamiltonians, if you're not a physicist, are really opaque because they sometimes appear in gates, they sometimes appear as observables. It's like a strange thing. In this case, your Hamiltonian appears as an observable. So because in quantum chemistry, very often you're interested in energy of a system, which is an eigenvalue of an observable, which is the Hamiltonian. So this is usually how I write it. And now the point is that often in chemistry, you're interested in, for example, finding the minimum energy. And what you would have to do, and I can't believe they're starting to draw outside. Oh my gosh. What you have to do is you have to, basically, if you minimize over all possible states here on these sides, so these are your quantum states, you can find the minimum energy of the Hamiltonian. And so the idea in near-term quantum computing is to do this variationally, which means with parameterized circuits. So let me just like try to introduce this here. Instead of minimizing over your states, you minimize over parameters. And so you know that you find at least something that's larger than the minimum energy. And if you're lucky, you get the ground state. And in our pictures, this is actually nothing else than just a circuit like this. So you have this variation circuit that prepares the state, and then you measure the Hamiltonian. Now, one thing that's important here is that rarely you measure the Hamiltonian as such, but you measure local Hamiltonians. So VQE is an idea of measuring lots of circuits and then combining basically lots of circuits that are themselves averages and then combining them linearly. So this is a really beautiful example how quantum computing is never just a quantum circuit. It's usually quantum classical anyways. Then briefly, let me just say a few words about optimization. So you can do the same principle that's basically written here if you're not a chemist or don't want to do VQE, but to solve optimization problems. And this is applications in finance, in logistics, anywhere you can plug them in and put a quantum in front of. So what you have here is that your Hamiltonian doesn't encode a molecule or chemical system, but your Hamiltonian encodes a problem, often a combinatorial problem, optimization problem. And again, you optimize some circuits to kind of solve it. And one of them that has basically kicked the near-term optimization field off in some sense is QAOA, sometimes called quantum alternating operator ansatz or quantum approximate optimization algorithm. It's the only short form that has actually two interpretations that I know. And so your problem Hamiltonian, I just gave you an example, is basically a diagonal matrix that contains solution or cost function values on the diagonal. And these cost function values correspond to bit strings. So this diagonal of a Hamiltonian corresponds basically to configurations of your quantum bits. So this one would say that the cost function of 0000 state is 3, of 001 state is 1, and so on and so forth. And now if you just go back and you say you plug this in here, and now you optimize a quantum state. I know there's a couple of jumps to go here, but basically the quantum state that optimizes this problem would be the one that has a lot of weight, a lot of probability in the large values. And this is this idea of creating quantum states that have very large probabilities at the values where the cost function is large. Large here because here we are actually maximizing traditionally. And now what all this other stuff here means is basically just, here now you do something that can be very confusing. This is your C is now your new Hamiltonian, but you also use it in your circuit. So you have basically a quantum circuit that depends somehow on this Hamiltonian, and then you have another Hamiltonian and a quantum circuit depends on this one. You can think of this as a time evolution that has something to do with your cost function, and this one a time evolution that kind of scrambles things a little bit. And then what you do in the quantum approximate optimization algorithm is basically just the circuit that applies them one after the other. And each time you apply them, you have a different parameter. So these layers here are parameterized, and then you train the whole thing and you can solve your optimization problem. And then lastly, I'm almost done, is machine learning. So I could talk probably for 100 years about quantum machine learning, but just also a quick flavor. So Penny Lane is based on machine learning tools, but it also can solve quantum machine learning problems. In machine learning tradition, you've got data, you've got a model, can be a model. So the model somehow reproduces the data. So if you have a problem of inputs to outputs, so your data are inputs, data and output labels, that will be a function mapping them, but it could also be a probability distribution. Then you've got a cost function that tells you how well is your model doing on the data. The goal of machine learning is to use data samples to find the model that minimizes the cost on unseen data. So there's a twist. You want to be good on data you've never seen, basically. But this is kind of like, people forget about this very often, because what we do in practice, we find the model that minimizes the cost on the data samples. So this is basically the proxy problem. So if you train models on training data, this is a proxy problem for training models or for constructing models that do well on test data in some sense. So this is the whole idea of machine learning. And how do near-term quantum computers fit in here? You basically just replace the model by a quantum circuit. So if you have a neural networks, now you have a neural network, for example, in TensorFlow. This is very elegant because TensorFlow and PyTorch and all of those were made for machine learning. You unplug your model and you just put in a quantum circuit. And then you get a quantum machine learning model. This is now an example for a quantum machine learning model that does this thing of like putting out outputs and taking inputs. So it's not a generative, but a discriminative or a deterministic model. And what you have here is an encoding. So the thing that you haven't seen before here is that you have to encode your data somehow. So quantum machine learning has a lot to do with this encoding. It's also called embedding. I think these are the same words as far as I'm concerned, where you embed or encode data into the circuit. And this encoding step maps the data to these high dimensional spaces. And you can think of machine learning by just like kind of like the measurement discriminating data in this high dimensional space. I actually made an example that was coded up with PennyLane, and I think QTip I used, where you encode data with a circuit, then you do your variation circuit turns it, and then you measure, and the measurement introduces this kind of function on your sphere that has a decision boundary there where it's wide. So it's the idea of variation in quantum machine learning models. And everything I just want to say about this is if you want to do quantum machine learning for your hackathon, think of the embedding. There's more and more evidence in the last couple of years, and I'm a big fan of like preaching this as well. The way you embed your data, this is what you get out of your quantum machine learning model. So if it doesn't work, maybe the embedding is not right. Okay, cool. That's it. Paul, I hope it wasn't too bad with the Wi-Fi connection.
Not bad at all. Not bad at all. Thank you so much, Ria. That was fantastic. Fantastic. I love a talk that references Wikipedia as one of its main sources.
Should never do that, right? I stopped our presentation, right?
Either way, if you stop it, we probably can't go back to look at any of the slides, but I don't have any particular questions about any specific slides, so that's great.
I'll dance my slides if anyone asks.
So great responses in the chat. People really liking this talk. A lot of great questions. I think we're going to have to, we're not going to pull any punches at this year's QHack. We're going to go straight for the hard questions here. Here goes. Ready? What problems cannot be solved by machine learning, but can be solved by quantum machine learning? Or to put another way, is there something that quantum machine learning is way better at or can do that machine learning can't do?
Yes. So there's a simple answer to this question and a difficult answer. The simple answer is just take a quantum algorithm that basically is already been proven to be classically intractable, plug it into a machine learning algorithm or in the way data is generated. For example, think of data I'm very sloppy here, generated by Schuld's algorithm or by discrete logarithm problem, something like that. So there were papers like that. And then do machine learning. Then you are by design, you can be relatively sure, although it's actually quite hard to show in the end because you have to show like there's no learner that can also do it. It's all heuristic and so on and so forth. But then you can show that there's this thing. Our problem is to find those applications that are useful. And this is really hard. To find useful machine learning applications that are classically hard is still an open problem. But we're slowly tracking it down. So people are chipping away from all sides to find out what is this quantum machine learning as well. And if I may just like add, I'm very probably unpopular with my colleagues in this regard, but I really personally don't find that question so interesting. It sounds strange, right? But I personally find the question interesting of what model class is quantum machine learning? How can it generalize? So let's describe what it is before we kind of put it immediately to the test of time of if there's no exponential speed up, I'm not even reading this. So that's kind of my approach to the question.
Okay, interesting. Yeah, that's very interesting answer to that. I think that'll satisfy a few people in the chat. Maybe not. We might have to revisit this at some point.
I'm looking for a challenge.
I guess another thing, we're going to probably, there are a few more talks coming up on PennyLane, but maybe it's a good idea now to say something about generally, like, is PennyLane an interface that can interact with many quantum computing systems? Like Qiskit, Google, Turk. Is it? Do you need to learn those other languages to work with PennyLane? How does that work?
Yes. So the answer is yes. The first answer is yes. So PennyLane is basically just you can think of it as a management system. On the one side, it dispatches things and uses quantum libraries, and it could be Cirq, Qiskit, anything like Amazon Bracket, so all the plugins that we have, and you can code your own. And on the other side, it has the classical machine learning framework. So in some sense, it connects the two through the idea of gradients. And then the second answer is you do not have to learn that other language, because how you would code up your circuits would be in the penny lane language, like natively. But if you have, for example, special syntax or building Hamiltonians or something like that in your personal library, you can very often use this with penny lane in some interaction interface as well.
Okay, there's another follow-up question. Just gonna scroll back and find it. Let's see here. Oh, is penny lane good for NISQ-based algorithms only?
Yes and no. So it's designed for NISQ-based algorithms, and usually what a software library is designed for, it's best at, right? Like you cannot often take it and check it with other things or hold it against other things. But you can do, in principle, a lot of things just with general circuits. So you've got gates, you've got measurements, you just can code things up. So I use mostly penny lane, not for variational or near-term algorithms, but I literally just prototype and I support my research, or I try to figure out, try to get implementations for research questions I have. So half and half,
A really important question. If someone is going to make penny lane 2.0, what Beatles song is it going to be named after?
Oh no. Okay, so I have to confess, I confessed it before, so I almost got fired for that. I really don't like Beatles, and so Xanadu is a free company and everything is happy, but you always have to refer to the Beatles. No, I'm joking. I love the penny lane name though. Before we called it OpenQML, which is kind of a bit more lame. So yeah, Yellow Submarine. Do we have Yellow Submarine already? I don't know.
Good question.
Maybe we should do. Maybe we should do. Oh, let's do a poll about this question with the audience, if that's possible.
That's a great idea. Sure, I think it is. Anything's possible if you can imagine it. So let's go ahead. All right, chat. What do you think? What should we name penny lane 2.0? Let's stick with Beatles songs just to keep it contained. But while those are coming in, Maria, what band would you like to name all of our Xanadu products after?
Oh gosh, so you mentioned that I was a metal fan when I was younger, and I totally changed sides, and now I listen to extremely weird music, like German chanson type of things. So I don't know if something like Giorgetti or I don't know is kind of useful here. So I pass on that question, sorry.
Okay, that's okay. That's totally acceptable. What do we got? Oh man, there's so many great questions coming in from the chat. More general ones. I mean, I'm sure there's a lot of people that are new to QML that are just getting started and curious about moving forward in this space. And so, how about what mathematical tools are required, for example, to master QML?
Yes. Well, there's the ML side and the QML side. So for quantum computing, mostly you'll be fine with linear algebra. And by linear algebra, I mean actually two different things. You can do quantum computing probably your entire life on some level if you just know linear algebra in terms of matrix multiplication with vectors. But there's a deeper meaning of linear algebra, right? A vector space is something that's more than just like a vector, but functions can be living in a vector space and stuff. And I find personally that if you want to do quantum machine learning, it's really useful to understand these abstractions as well. Not understand them, but maybe be curious about them. So, for example, I do a lot of research at the moment, and my colleagues are hating this as well because I'm always preaching everything about kernel methods. So kernel methods is something, if you have heard of an SVM, support vector machine, and I'm very much convinced that variational quantum circuits are very similar to support vector machines, if you can't even say there are support vector machines in a certain sense. And so these support vector machines are linked to, you can just learn them as machine learning, you just use them, you have your coding paradigm. But if you really want to dive deep, then you happen to work in reproducing kernel Hilbert spaces and stuff like that. And then linear algebra kicks in. And I personally still find it strange to look at a vector and think of it as a function and whatever. But so that's the next level then. But the lower level is matrix vector multiplication gets you everywhere.
Okay, I got that. I know where to go now. Let's see what else. A question for you. If you were able to kind of go back in time and meet your young self starting out on this road, is there any advice you'd give yourself for don't say stop and don't do it.
No. I really love it. I actually almost ended up, it's total coincidence that I ended up in science. I applied to lots of different jobs in my master's and nothing had to do with science. And then I didn't get a lot of the jobs, so I kind of did my PhD. So it was total coincidence. So I was actually able to do really follow the stuff I wanted to do because I thought I would never stick around for long anyways. So in terms of topic, there wouldn't be anything like that. But there's a lot about research, and that is the following. And I think those of you who code a lot know this already. Research is a cycle of frustration and euphoric moments. So I don't know if this is a woman's thing. No, I don't know. Like, but I think, so for me, research is really like those moments of being super convinced this will work. And then you start the first step, and the first step happens, you walk against a wall and you're just like, this doesn't work. Why did I do this in the first place? How can I ever finish this? And if you have a very low self-confidence, this is actually dangerous for you because you might stop. If you have a good self-confidence, you're like, easy, have always been good at school and stuff, then maybe you continue easier. But however, after that, you go the next step and you manage to like keep on. And then all of a sudden you understand something. And then it becomes like, now I could do this. And then you hit the next wall. So the one thing I wish someone would have told me when I started is that these walls, and sometimes they take months, when you get older, they get easier, they get less painful, and you see, oh, it's my old friend. And if it doesn't happen, maybe your research question is not hard enough, actually. So you start playing with this feeling a lot. So that's the one thing.
Okay, it's not unique to you. I totally understand this. I've heard many people refer to it as, it's like a sine function. You have these peaks and troughs, but I've also, I think, more correctly heard it referred to actually as a sequence of delta functions. It's nothing, and then complete breakthrough euphoria, and then a bunch of nothing again. And that, I think, is more. Yeah.
There's another tip. If you have the euphoria, so the delta function peak on a Friday, stop immediately and go into the weekend, because the next step that happens will break it. Or if you run a program and you just manage to do it well and it's running, don't change the next line of code, just go home.
So yes, I'm writing this down. That is fantastic, actually, advice.
Are you making notes, Paul?
Yes, that one's a keeper for sure. Okay, I still don't see any I actually don't have eyes on the live chat, so I don't know what is leading right now for Penny Lane 2.0 name, but we'll come back to that in a minute. Let's see. Oh, so many great questions. I'm not even sure where to go. I want to ask more about Maria. I just want to chat, and since we have you here and your Wi-Fi is actually working. So what is it like living in South Africa? We have so many people from all over the world joining us for QHack. Maybe you could tell us a little bit about what it's like where you are.
Yes, so except from Wi-Fi issues and that our electricity sometimes goes down. So my biggest nightmare was actually that there's a government load shedding outage. So I would be like half of our team, I think that is in South US at the moment, like we'll be out of power. But I guess we cope. Living in South Africa is just amazing. I kind of like refuse to be anywhere else. I guess some people just like go somewhere. So I grew up in Germany and then I went to South Africa only when I was 23, and just from the day I came here, it was like a thing of like, I'll stay here. I don't know why. And have since actually really refused or resisted, the drag or the pull to get a better life somewhere else, less issues, less problems, things are working better, my Wi-Fi is better, or things like that. And I cannot really tell you why. I'm thinking about this all the time. One of the reasons is obviously because it's a beautiful country with wonderful people and blah, 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 blah. I mean, this morning I spent surfing for an hour and the dolphins jumped in my wave. I'm not joking, which was amazing. But then the other reason is also like that so as scientists, I think there's a scientist part to this. So as scientists, we love challenges. We love to be taken out of our comfort zone and exposed to complexities. And I find living in South Africa as opposed to living in Germany means you're constantly in a political sphere where your actions are extremely complex and they have a historical meaning and they have a future meaning. And I think I find this challenge really interesting because I think it's everywhere in the world, but in a few countries you see it every day. And yeah, I think this is a very interesting conversation to have and a challenge to have. And yeah.
Wow, that's super cool. Yeah, it's one of the top countries on my list to visit once I can start traveling again.
Everyone's invited. Well, I don't know how many people are watching, so but
you heard it here. Everyone's invited. Can't take it back. What's your address? Let everyone know. Oh, so update. It looks like so far, Hey Jude is leading the polls for Penny Lane 2.0. I personally love that song. Great song. Great choice. Let's see.
We could also just keep Penny Lane. I don't know if that's one of the options.
I think that's definitely an option. But why keep it? I mean, why not? When PennyLane 2.0 sounds, just as boring as Open QML, I think we should go with.
That's true, but we're finally getting a professional logo at some stage. So those of you who use PennyLane realize there's always different like pictures that we put with it, and they're all like hand drawn in some way. So if we get a nice logo, then we have to unfortunately keep the name because,
That's a good point. Spoiler alert! I don't know. This is breaking news that we are getting a new PennyLane logo.
What's the rumors?
For that. Actually, funny. Another little factoid, another breaking here is that our founder Christian Wiebrook, his favorite song is actually "Hey Jude" as well. So not sure if they knew that in the chat or just coincidence, but
it's him.
Yeah, maybe. Yeah. That could very well be. So maybe going back to some more like educational stuff. I think this is a great opportunity for us to talk to people getting started again. Could you say anything for like specifically high school students, maybe like at that level that's looking to get into quantum computing and QML? Because kids are starting earlier and earlier these days with learning these concepts. What advice would you maybe have for them on getting started?
Yes, so a couple of years ago, it was actually not so easy. I think you would have to have undergrad physics knowledge or something like that, especially the companies. So especially like startups, so Xanadu, but also obviously like IBM with the Qiskit community outreach have provided a lot of information online. So just by looking into the software libraries, you can get so much information, and everyone's really trying to make it accessible and easy, because what we want to do is we want to get lots of people to play with this stuff. So I think on the side of like learning this, you should be fine just looking on the internet. However, so there's one thing about high school students. So if you don't have a PhD, basically, I think a PhD gives you, after going through all these cycles of frustration, gives you this idea of to take research serious. And in some sense, especially when you do machine learning, people often just sit down and they just try. Which is nice, right? But the next step to trying is thinking, what's actually happening here? So when you have a small circuit, get a toy model and calculate what's happening. Calculate what's actually in there. Don't think quantum is just magic. It's just a matrix vector multiplication in the end. And this matrix vector multiplication can lead to extremely boring functions. So for example, you can do quantum machine learning with classically intractable circuits, but have models that are as stupid as a sine function. So you have to be really careful what's happening there. So that's the idea. Like, don't be scared of really asking what's the math behind it, and don't be too stunned by quantum, because in the end, the difference between quantum and classical is very small and very hard to find. And but what quantum is actually quite interesting for other reasons as well.
I like that. No pun intended. The difference between quantum and classical being small. But yeah, I think that's a great point, saying that it's not magic, right? This is science. There are rules. You can learn them. It's not out of people's reach, especially.
I never understood the saying that if you think you understand quantum mechanics, you didn't understand it. So I never understood this saying, because I always thought there's rules, it's maths, and you can see how it works, right? That you can't interpret it is a completely different question. But you don't need this interpretation to work in it, right?
Well, that's just it, right? There's just the bizarreness of quantum phenomena, right? This idea that is the particle really a wave or a particle?
Yes. So the interpretation.
You don't care to do the quantum. Yeah, the interpretation part is magic. The phrase "shut up and calculate" comes to mind for me when it comes to this stuff, right? Let's see. So we could spend another couple hours here. We're getting close to the end, so I do want to make sure we cover some of the burning questions in the chat. See, should we ask more about education, or maybe some more general? I want to ask Maria more stuff about Maria. So what research areas are you focused on right now, Maria? You talked a little bit about what's got you excited, but right now, what are you working on?
Yes, so I've got basically two questions, or let's say one question. No, two questions. So the one has to do with these kernel theories. So I'm always doing quantum machine learning. Maybe that's my biggest sin, that I'm doing quantum machine learning since I started my master's. So I've never done anything else, which is sometimes a bit sad, but sometimes also quite powerful. But so one of the big questions that's still unresolved is the question of how these kernel methods and this interplay actually works out. So what does this mean about quantum learning? In some sense, you can say, if we interpret quantum machine learning models as kernel methods, I know I'm saying a couple of vocab here that almost no one might be able to put together, but just saying if we can unite these things how we are doing it at the moment, then actually the whole idea of what's learnable becomes only a very small computation. So think of a huge quantum machine learning algorithm, and this link now tells you that the only thing that actually your quantum computer has to do is, and now I tell you the technical idea, like measure the overlap of data in Hilbert space in some sense. So just get state overlaps. Everything else is just decoration in some sense. You can, like, in many cases, not in all cases. So for those of you listening, know what I'm talking about. In generative models, we don't really know what's going on. Alejandro will probably talk about this because he sent me an email, like, we're discussing it. But yeah, so the idea that in a lot of models, the quantum computation part can be reduced to a minimum. So what does this mean for us? So that's a big question. Second question, I mentioned in this machine learning slide, and that took me years to figure out properly or understand properly, machine learning is not the task of optimizing a model on your training set. Machine learning is the task of generalizing well. And so how can we phrase, understand, model, query, benchmark the question of generalization in a quantum setting? So for example, do we see the same things like in deep learning, that generalization gets worse when you increase your model size, and then all of a sudden it gets better, and then the bigger the model, the better? So this is called double descent curves, for example. So all these phenomena we know from classical machine learning that are really puzzling people at the moment. What happens then in the quantum regime? So that's the second big question, if that made any sense.
That made a lot of sense to me. Yeah, that's fantastic. Cool, very cool. I'm really excited to see where this field is going. Looking forward to your next paper as well. Yeah, Maria, thank you so much for joining us. I'm so glad that your Wi-Fi stuck it out for most of the of the session. Yeah, again, thank you so much. This has been fantastic. We're going to take a quick break now and get set up for the next talk at 9 o'clock. Again, thank you so much, Maria. We'll be right back. Don't go anywhere, anybody.